Okay, thank you very much all for coming. So this is part of the work I'm doing with Holger at the Ruhr University in Bochum, Germany. And here we consider the case where not only the response but also the covariates in a model are subject to errors. And so we use the class of errors in variables models. So first I will introduce the main characteristics of this class of models and then present general estimation and optimal design results we have, followed by results on de-optimal designs for specific nonlinear models, which we then apply to data examples from the literature. So errors in variables models are basically regression models, but one or more of the covariates involved in a model cannot be observed exactly. So to define these models, we begin with an underlying model of the response with respect to the true variable x for the covariates. But instead of x, one can only observe another variable w, which is called the observed variable. And the relationship between w and x is described in the error model, which either specifies the conditional distribution of x given w or the distribution of w given x. So we basically want to estimate the parameters of the underlying model, but we can only fit a model of the response with respect to the observed variable w. Now the classification of these models is based on two characteristics. The first one is determined by the properties of the true variable x. And we have a functional model if the true values of the x are fixed constants, and a structural model if the x's are treated as random variables. Then the second characteristic is the structure of the error model. And we have a classical error model if we specify the distribution of w given x, and the covariate errors epsilon are independent of x. And then in a Bergson error model, we specify x given w, and the errors are independent of the observed variable w. And in both cases, the most common form of the errors is to have a simple additive error on the covariate. Now, in order to choose the model to use in an experiment, we need to take into account the experimental conditions and the available data. So generally speaking, if we have a random sample from a population, we use a structural model. Otherwise, we use a functional model. However, functional models are preferred because we make no assumptions on the distribution of the true variable x. And so we avoid any robustness issues we would have if this assumed distribution is misspecified. Now, a classical error model is appropriate in an experiment where one is unable to determine x because of errors in measurement. And these errors include the sampling error and instrument recording error. So if our x is the true intensity of an X-ray beam, then we would have errors due to the instrument used to measure this intensity, and of course these errors are independent of x, and therefore we have a classical error model. Now in a Bergson error model, the errors come through the setting of the covariate values x. And usually the error due to measurement is assumed to be 0. And these include errors in application or errors due to physical phenomena. So if we have x to be the true amount of water absorbed by a plant, all we know is how much water we applied to the plant, and that will be the observed variable w. So the errors can come either from fluctuations in the water pressure or because of the absorption process itself, or from both. In any case, the epsilon is not independent of x because, for example, if we have fluctuations in the water pressure, then of course these will affect how much water the plant will actually absorb. So generally speaking, if we ignore the error in the covariate, we would get biased parameter estimates. And of course, the exact effect depends on the assumed underlying model, on the structure of the error model, and the assumed distribution for the errors. In the case of a linear regression model, this effect is known as attenuation to the null, because the least squares estimate for the slope is biased towards 0. Now, there is a large literature on data analysis strategies using all these errors in variables models, and these are just 3 books that have quite a lot of examples of situations where you would use an error in variable model and a lot of estimation results. The last book, the book by Fuller, is more focused on classical error models, and the book by Carroll et al. Is focused more on Bergson error models. We consider nonlinear underlying models. Theta is the parameter vector, eta is the response error, the usual error we assume in a model equation, and the unobserved true values xi are treated as unknown fixed constants. So here we have we adopt the functional approach. For the error model, we assume classical additive errors. And at this point, we also introduce the design setup by considering repeated observations. So n is the number of distinct experimental conditions, and Ri is the number of repeated observations at the experimental point xi. We assume that the underlying model function m is continuous with continuous first and second order derivatives, and that the vectors for the response error eta and covariate error epsilon are IID normally distributed with 0 mean and fixed positive definite variance covariance matrix. Now, the third assumption is an identifiability assumption, so that the difference theta minus theta true can be detected. And these assumptions follow the ones used by Fuller, who also consider nonlinear functional models with classical additive errors, but he fixes the Ri's to be equal to 1, and he finds the limiting properties of the maximum likelihood estimator as the error variances become small. So to relate his result to our repeated observations setup, we take omega I to be the limit of Ri over R, where R is the total number of observations, and we gather this information in an approximate design. So following Fuller's methodology, we find the asymptotic properties of both the maximum likelihood and the ordinary least squares estimator as the sample size increases. In particular, we showed that the maximum likelihood estimator has a limiting normal distribution. It is an unbiased estimator for the true parameter vector, and the information matrix differs from the classical one only through the function sigma 1, which involves the variance covariance matrix of the errors. Then similarly, we showed that the least squares estimator also has a limiting normal distribution, and now the information matrix involves both the sigma 1 function and another function sigma 0, both of which are given by the last expression. So to understand what these two sigma functions represent, let's consider the linear regression model with classical additive errors, and let's also assume that the two errors, the response and the covariate error, are also non-correlated. Then these are the expressions for sigma 0 and sigma 1, and they both involve the vector 1 theta 1, which shows how the response and the covariate enter the model equation. And so the sigma 1 function, which is the only one involving the variance-covariance matrix for the errors, shows how these variances will enter the model. And particularly for the linear regression model, sigma 1 is the variance of the new error term we would get if we just substitute W for X. Now, in the case of maximum likelihood estimation, the general equivalence theorem holds, and this is the necessary and sufficient condition for the optimality. But of course, in the case of least squares estimation, the general equivalence theorem doesn't hold because of the form of the information matrix, which leads to non-concave optimization problems. So we only have a necessary but not sufficient condition for the optimality. Generalized versions of this result and the previous result for maximum likelihood estimation are proven for phi L criteria. So these results are actually applicable to many criteria and not just the optimality. So to get any analytical results on the d-optimal designs, we need to specify the underlying model. And we consider the Michaelis-Menten, the Emacs, and the 3-parameter exponential regression model, which of course these models are very often used in modeling the dose-response relationship. In this case, theta 0 is the placebo effect. Also, the parameter theta 1 is involved in the placebo effects in the case of the 3-parameter exponential regression model, and it is the maximum achievable response for the Michaelis-Menten and Emacs model. And then the parameter theta 2 is the dose producing half of the maximum response for the first two models, and it describes the dose effect for the exponential regression model. So we have nonlinear functional models, but here we consider that the model has only one covariate. Again, we have classical additive errors, and we also add the assumption on the normally distributed errors that these are non-correlated. So using the general equivalence theorem, we proved that in the case of maximum likelihood estimation, the d-optimal designs are saturated for all three models, and so they are equally weighted. Whereas in the case of least squares estimation, we used the necessary condition to find upper bounds for this number of support points. And this bound is equal to 4 for the Michaelis-Menten model, equal to 5 for the Emacs model, and for the 3-parameter exponential regression model, the design can have up to 6 support points. So it turns out that the general characteristics of the classical d-optimal designs for these models still remain in the case where we also take into account the error in the covariate. And in particular for the Michaelis-Menten model and also maximum likelihood estimation, the design is always supported at the upper bound xu of the design space, and then the smaller support point is always larger than 0, so no observations at point 0 can be taken. And this is also the case assuming no error in the covariate. However, the difference here is that the non-trivial support point x star is the solution of the given equation, which involves the parameter rho epsilon eta squared. And this is the ratio of the variance of the covariate error over the variance of the response error. So if we take rho to be equal to 0, we get the usual design available in the literature for no error in the covariate, and then this x star increases as the value of rho gets larger. So the design moves, well, the non-trivial support point of the design moves further away from the corresponding one for the design assuming no error in the covariate. And the limiting value of this x star is just xu over 2, where xu is the upper bound of the design space. In the case of the Emacs model, again, we have a saturated design supported now at both endpoints 0 and xu. And the middle point x star is actually the same as the corresponding one for the Michaelis-Menten model. So it has the same properties, and it increases as the raw value increases. This is the result for the exponential regression model. Again, we have a 3-point design supported at 0 and xu. And the middle point x star, again, depends on the raw value and increases as the raw value gets larger. Now, in the case of least squares estimation, of course, we don't know the exact number of support points, but we consider the construction of saturated designs in order to compare the two estimation methods. So for the Michaelis-Menten and Emacs model, we have the same properties as for the maximum likelihood estimation case, and the common point x star, which is the same for both models, is found by solving the same equation as before, plus an extra term. And this extra term results in the x star for least squares estimation to be always larger than the corresponding x star for maximum likelihood estimation. In the case of the 3-parameter exponential regression model, the results are not exactly the same, because now the design is only supported on the upper bound and not necessarily on the lower bound 0. So the other 2 points have to be found numerically. So to illustrate all of these theoretical results, we use data examples from the literature. And in these examples, we compare the two estimation methods. We find the efficiencies of the d-optimal design assuming no error in the covariates. We investigate the sensitivity of our designs when the parameters are misspecified. And finally, we consider the construction of non-saturated designs for the case of least squares estimation. So the first example we consider is discussed by Mihara et al. And they study the velocity of a biochemical reaction, how this is affected by the concentration of the substrate. And they model this using the Michaelis-Menten model. In their setup, the design space is the interval from 0 to 80, and they obtain the parameter estimates 16 for theta 1 and 3.5 for theta 2. So any possible instrument recording errors are, of course, errors in measurement, and so we can apply our results for the Michaelis-Menten model. So the table gives the smaller support point x star of the d-optimal design in the case of maximum likelihood and least squares estimation, and for various values of the parameter rho. The upper support point is always 80, so it's not included here. So as it was shown from our theoretical results, the x star for least squares estimation is always larger than the corresponding one for maximum likelihood estimation, and x star increases with the raw value. So as the ratio of the variances increases, then the design moves further away from point 0. Now, usually we assume that the error in the covariate is small, and so we just ignore it in the design stage. For the values of this experiment, that design, assuming no error in the covariates, will be equally supported at points 3.22 and 80. And the table gives the efficiencies of this design under both estimation methods and for various raw values. Now, the efficiencies are very small, particularly for least squares estimation, and they become larger than 90% only if rho is smaller than 1. So only if the variance of the covariate error is small, but small compared to the variance of the response error. So just by assuming that sigma epsilon square is small doesn't necessarily mean that the design will be efficient, because here in the case of rho equals 1, so we have a small error in the covariate and an equally small error in the response, still the design is not efficient. So for our second example, we use the data by Frizzolo and Stewart, who study the wave velocity in rocks against the percent gas saturation. And this percentage is determined by an absorption technique where the rock is scanned and the intensity of an X-ray beam is measured. And as before, we have errors due to the instrument used to measure this intensity, which corresponds to the case of classical errors. Now, the technique they used to get these saturation levels could only produce levels up to 35%, and that's why we have a design space from 0 to 35 and not 0 to 100%. So for their data, we assumed that the two error variances are equal, and we fitted the 3-parameter exponential regression model and obtained estimates for the model parameters and also an estimate for the common variance sigma square. So for these values, the locally d-optimal design, including the error in the covariates for the maximum likelihood estimation, is given by Xi1, and the corresponding saturated design for least squares estimation is given by Xi2, and the table gives the efficiencies of these two designs when the parameters are misspecified. Theta 0 doesn't affect the design, so that's why it's not included. And then we took all the possible cases of the two parameters, theta 1 and theta 2, and the common variance sigma square, all of this being misspecified by plus or minus 10% or 30%. And we can see that the efficiencies are well above 90%. So unless the nominal values used are too far away from the true, let's say, values, then the designs are efficient. These are the locally optimal designs. So finally, for both of our examples, we consider the construction of non-saturated designs for least squares, but it turns out that for these examples, the locally d-optimal saturated designs are actually globally optimal. We cannot prove this, but for the two specific examples, this is the case. So we have developed an approximate design theory for nonlinear functional models with classical additive errors, both for maximum likelihood and least squares estimation, and found analytical characterizations of the designs, of the optimal designs for specific nonlinear models. And from these characterizations and the data examples we consider, we showed that the design assuming no error in the covariate is not always, is not necessarily efficient, and one has to compare this variance with the variance of the response error to decide whether we ignore this error or not. And we also showed that the locally d-optimal designs are actually the d-optimal saturated designs are globally optimal for both estimation methods and also robust to misspecifications up to 30%. Thank you very much.
Any questions or comments?
Thanks for the nice talk. The third conclusion that you had there, I was interested in. So I I think you got that from the first example where you looked at when the ratio is 1 to 1, that there was low efficiency if you ignored the error of the covariate. What I was wondering is, when you did that test, did you assume that when you were ignoring the covariate, ignoring the error on the covariate, that the error was then pushed onto the error in the entire measurement? Because that's what you sort of expect if you're not taking into account covariate error, that the overall error of the total model increases.
No, you just have the error in the response, because
Right, so but that error, if you estimate that error without assuming error in covariates, you would assume that error would increase.
I'm sorry.
So if you assume there's no error in covariates, you estimate your model and the error associated with that
The
model.
response error,
The response error should be larger.
But it doesn't make a difference here, because rho is the sigma epsilon square divided by sigma eta square. So sigma epsilon is the covariate error.
Yep.
Okay, so here I include both. If I assume there is no error in the covariate, then this rho becomes 0, and it's the usual design. So no matter what the response error, big or small.
But aren't you assuming that the rho then for the response error is the same? You're not increasing that error because
The rho is 0 if we assume no error in the covariates.
what you're saying here is that if you assume there's no error, but there really is error, right? Is that what you're saying?
Yeah.
So if you assume there's no error in your covariates, but there really is, then you think you have a inefficient design. But it seems like what you've done is you've compared, okay, we have our optimal design for these two error terms, and then we set one error term to 0. What does the design look like? What is the efficiency of those two designs? Whereas I would think that the total response error should be increased to the sort of approximate amount of error you would estimate in a study where you assumed that there was no covariate error, but there really was.
But the classical design is not affected whether the response error, the usual equation error, is big or small. This is always that. Doesn't change.
Because it's additive error.
It's
Got
just-
it.
That's the classical design.
Okay, I understand.
The design changes only if you consider this error in the covariate, and it changes according to this rho value.
That's because the actual, then you start getting in proportional errors.
Exactly.
Any other questions? Yes.
I'm a little bit lost, so help me to understand. So what kind of design, what kind of error you consider when you do design? Do you consider Bergson model or functional model?
Classical error, sorry.
No,
So-
any design. When you are doing design with errors, are you talking about designs, optimal design for functional model or for Bergson model?
We have to specify two things. To define the model, we have to specify two things. One is whether it's functional or structural, and we take the functional case.
Yeah, I understand.
And then the other is classical or Bergson, and we take the classical, not the Bergson.
Not the Bergson.
No.
That's what somehow, you see, when people introduce functional model, it's assumed, at least implicitly, that you cannot control X. You just can observe it. And
Yes, you cannot
optimal,
control.
so how can you do design if you cannot control X? So that's somehow bothering me a little bit. Because from what I know, in all the times people did optimal design, but for Bergson model. And the basic idea was that you fix some X, you want to fix some X, say, pressure in your reactor or whatever, to 100 atmosphere. But you cannot, you try to do this, but in reality it happens to be different pressure in this. So at least you can approximately control what you are doing. So from my point of view, you can do design only for Bergson type of model. So it somehow contradicts with what you are saying. So you
The Bergson error model is specifically for the case where you go in application and you cannot, we gave a design and you cannot apply that design specifically. So if x is time and then the person, the experimenter,
Yeah.
doesn't go at a specific time, that's exactly Bergson error model. But in the Bergson error model, the error in measurement, for example, from the instruments, like this X-ray beam I said here, this is not considered in the Bergson error model. It's not very easy to distinguish which one of the two should be used, and I guess it depends on what you want to focus on. If you want to focus on error in measurement, then you should use the classical error model and not the Bergson one. But if you want to consider this error in application, then it's correct to consider the Bergson error model. That's how it is defined. It's the error in setting the values, whereas the other one is an error in measurement.
Okay. Then the second question. So you talk about least square estimators. So can you go to this slide? What kind of least square estimator?
Ordinary least squares.
Sorry?
Ordinary least squares, not weighted least
And
squares.
for which model do you use least square estimator? So you have
This
two
model.
for Bergson or for function?
This is the underlying model, functional model, because the x's are constants. And this is the error model. It's a classical error model. So if I had x and w reversed, then that would be Bergson error model and adding the assumption of independence. So the mathematical difference between the two models is this independence of the error. What is the error independent of? That's the mathematical difference, and that's how the information matrix comes in the end.
So you observed, so W.
I observe W, and I have, this is my unobserved X, and W is an unbiased estimate of the true X.
But in this case, least square method, you have to use so-called least distance method, not least squares. So in classical setting for functional model, it's for whatever error and variables models, you have to use least distance model, because in this case, y and x more or less on equal rights. If you write down really simple linear model, y and x on equal rights, and so that's why people maximize not residual, just vertical, but the distance from function, response function, which you fit it.
Okay, I'll have to look at that.
I think we've just followed Fuller's approach. So Fuller.
He has maximum likelihood only, yeah. We just use that.
Okay, but usually squares are not consistent there. That's what somehow, especially for nonlinear models.
Ryan, any
Okay.
questions?
Maybe Valeria stole my question. Well, I'm also scared a little bit about using the classical error variable model, because I wonder how you can perform it, how you can set x if you can observe it, if you can observe it only in a disturbed way by w.
Yeah.
And on the other hand, okay.
So because we consider the error in measurement, we have to take the classical approach.
Yeah.
It's this independence here. So if we use the other one, we will not have this independence, and it's wrong. When you have error in measurement, then this error is independent of x. So you begin with that. We have to use a classical error model. Okay. So in the last example with this X-ray beam, if we say we need the intensity to be, I don't know, 20 or whatever the number would be, then of course there will be an error in application. There will be some rounding. The experimenter will just shift it and have it like 19.8 and just say, okay, this is 20 or whatever. But then that's something we have to consider later on. But to begin with, when you consider errors in measurement, then the correct model to use is classical error model. And if everyone used Bergson error model, then it's like you never consider sampling error. Sampling error is classical error. So then how do you involve the sampling error in the design if you just only use Bergson error model, which is the error in application.
Sure, but I still have problem how to perform the design in practice.
Yeah, in practice, yeah. There will be an error in application in practice, for sure. Yeah, so then maybe the next thing is how do you combine the two approaches? Because one is for one thing and then the other is for something else, but in practice both of them happen simultaneously, of course.
Isn't it just an additive plus proportional error that you include then, instead of just an additive error?
Sorry?
Wouldn't that be one way to incorporate both problems? Or
Where?
am I missing something?
I think
They,
it seems to me Rainer has the same problem because in Bergson case, and it was specially invented for this situation, you can fix X at least approximately. You try to do something, well, unfortunately it's not there. But at least I have some control. And in functional model, which usually used in economics, for instance, you cannot control X, you just observe them. There's a relationship between X and Y, and both of them are observed with some errors, but you cannot control. So for me, I cannot grasp how you can do design for this model.
So I think that further discussion is to wait until after the session. We do have to move on to the next speaker, so let's thank Maria one more time.
thank you.